Hi, welcome to the QUT Introduction to Robotics MOOC, the second live event. Thanks very much to everybody who came along, attended the last one. Thanks to all those of you who are attending number two. What I want to do today is really just crank through some questions, some really good questions were left over from the first one, and a bunch more questions have come in since then. So what I'm going to do is just work through the questions like we did last time. Just before I do that, I'd just like to talk about what I'd like to do in event number 3, which will be in about a week's time. And what I'd like to do there is to shine a bit of a spotlight on the work that's happening in some of our groups, which is related to the project. There's a bunch of people we know who are building the robot using a mixture of technologies. There's an active Lego activity, and there's also an active activity using Arduino technology, Arduinos and various kinds of servo motors, standard RC servos, Dynamixel servos, and whatever. So over this coming week, I'd really like to hear from any of you who are involved in these groups, who've got something really cool to show. If you could perhaps contact us, contact moocs@qut.edu.au. Perhaps point us at some material that you've got up on YouTube. It could be a YouTube video which shows maybe a very short PowerPoint type presentation, the highlights of what you've been doing, but even better, show us the robot, show us what you've actually been able to build, and we'll share that with everybody else through the broadcast. And some of the tutoring team, James, Jack, and Obadiah, will come in and perhaps answer any questions that might arise. So let's get into the questions. The first question I've got is from Chris Sykes, and Chris asks, do I see the biggest problem with robotics and exploration as the extended power source? I.e., is there enough power for these devices? And it's a really good question, and there is a real problem, I think, with power sources for all sorts of devices. We're frustrated with how quickly our phones go flat, tablets go flat, and for robots which have to expend energy not just on thinking and sensing, but also on locomotion, battery life is a really, really big issue. If you've seen the Asimo robots, the small humanoid robots from Honda, you see that they wear these big backpacks, right? And the backpacks are essentially full of batteries, as I understand it. So the batteries are a really big issue. I did a few sums. This is something I looked at a while ago, and I just revisited the calculations that I did. If you've got a LiPo battery pack, a 3-cell battery pack, it might hold 87 kilojoules of energy when it's fully charged, and it weighs 200 grams. A cube of sugar weighs 4 grams and contains 68 kilojoules of energy. And so it's clearly an advantage that biological systems have. We can consume cubes of sugar, bread, chocolate, energy drinks, all of these sorts of things, and that's what gives us the energy to run. My brain consumes 18 watts continuously, and however many watts I need to move around the world. So clearly, biological systems have got the energy problem sorted. We've got a long way to go for robotics. I'm not sure if people are doing work on robotic stomachs. If you had a robot, then you could feed it bread and chocolate and energy drinks, and it would run. It might actually be some advantage in building such a thing, but I don't know of anybody doing work in that particular area. So bottom line, energy sources for robots is a really big problem. Jason Delancey asked a question. He listened to a podcast about zero tillage agriculture, and this is something I did for RoboHub last year. And in that, we were talking about robots that would go out into the field and destroy weeds. It seems perhaps a little bit trivial, but the reason farmers don't like weeds is within the soil there's only so much nutrition and so much water, and weeds take that nutrition and water, and that's then removed. That's not available to the crop, which is the thing that he wants to harvest and sell. So that's why farmers don't like weeds. So in that particular podcast, I was talking about using microwave energy to destroy the weeds. And Jason's question is, is there a problem with a microwave wielding robot going rogue without an e-stop? do we have teams of lawyers and safety experts? What sort of due diligence do we need when you're doing research in new areas to ensure that everybody's safe? Whenever you're doing experimentation on a new robotic system, particularly a field robotic system that's out in the real world, safety is really important. For our work at the moment with agricultural robots, we have wireless e-stop systems, so the robot is always under supervision. So if it goes crazy, we can stop it. The robot wielding microwave generators for destroying weeds. Microwave radiation is hazardous to humans in this particular robot, and we haven't built this yet. It's still something that we're thinking about. The microwave antennas, they're called horn antennas, so it's like a square funnel, and that would be pointing at the ground. So the microwave energy would be directed into the ground. So if we design it right, and design is always really important when you're trying to ensure safety of a system, if the funnels are always pointing at the ground, then the robot is going to be safe. The energy can't go into human beings, short of the robot tipping over on its side and those funnels being exposed. But then you could put sensors in the robot that could detect that the robot was not in its correct orientation. The whole issue of legislation and liability and litigation around robots causing accidents is still something I don't think as a society we have got our head around. It's a really important topic, actually, and we touch on it a bit in the very last lecture in this course. Lecture number 12 is about ethical issues associated with the use of robots in society, and safety and liability is something that we touch on there. But I don't have an answer for it. All I can think is that this technology, I think, is going to be incredibly valuable to people in the agricultural industry, and if there are ambiguities in the law that prevent us from using the technology, then our societies, our governments will change the laws that will, so as to enable these productive robots to come into use. I mean, once upon a time, there were probably no laws about motor cars. Motor cars hadn't been invented, but they were really useful things, and they probably caused some legal conundrum in their day, and laws were changed to recognize motor cars and deal with the issues that arise. And it's my belief that exactly the same thing will happen for robotics. So there's a precedent for this introduction of a new technology. Paul Faria asks a question. He says that he works as a software engineer, and he's wondering if there are any open source projects that I'd like people to put their efforts into. I think it's a really great aspiration to want to put your time, your effort into open source projects. I'm not going to recommend any particular open source project. I think if you want to contribute to an open source project, it's got to be something that you personally believe in and want to see grow and improve. So I'm not going to tell you what project you should work in, but if you are that way motivated to put your effort into open source software, I think is a fantastic thing. And it's actually very, very rewarding if you create open source software that lots of people use. You'll get emails and people will complain that it doesn't do this and it doesn't do that, and that's a bit frustrating. But you also get lots of emails just out of the blue from people who say, this is really great, thanks for writing the software, it was really useful. And with my own open source software, the MATLAB toolbox that many of you are using, the robotics toolbox, I first started writing that when I did doing my PhD, I think 1992 or 1993, and I go to robotic conferences and people come up to me and thank me for writing the toolbox, and it's a nice thing, makes me feel very happy. So go open source, but your choice as to what project you devote your time to. Okay, a couple of kind of related questions from Rob Gannon and Magdi. And one of the questions are really around MATLAB. Is MATLAB actually a suitable environment for controlling real robots, or is it only useful for learning about robots? Now, that's a really good question. I certainly think MATLAB is a really good language for learning about robots. And what I like about MATLAB, about working in MATLAB, is that it is a very it's a very powerful environment in which to work. With just a few functions, a few lines of code, you can get an awful lot done. The fact that you don't have to compile and link the code before you run it means that you can just work interactively within the MATLAB console. And that's how I do most of my work. I work in the console, I develop code incrementally, and then eventually I cut and paste it out of the console into an editing window and tidy it up. So I start by exploring interactively, and MATLAB is just wonderful for that. Fantastic graphics, great displays, and then eventually I turn it into a function, a reusable function. For real robots, MATLAB is perhaps a bit more problematic, but there's some really good developments happening with the MATLAB product that I'll share with you in a moment. So if you want to use a small computer like, say, an Arduino or a Raspberry Pi, then you're not going to find a version of MATLAB that will run on that particular platform. To write robot control program on those small platforms, you're going to be writing it in C or C++ or perhaps in Python. But what's happening with MATLAB at the moment is it is developing some quite good capabilities for code generation. So you can actually write code in Simulink, and Simulink is the graphical block diagram language, or environment rather, that's part of MATLAB. So you can draw a bunch of blocks and wire them up, and you can put code in those blocks or MATLAB functions or whatever. And then you can ask Simulink to export that as executable code. So it will compile a diagram into code and push that into a piece of hardware. And they have hardware support packages now for Raspberry Pis and for Arduino, and I think for Android phones and a bunch of other platforms. So you can write code in MATLAB, export it as a runtime into those other environments. So it produces, quite time efficient runtime code. And I've experimented with this capability, and it works as advertised. Now, another part of the question from these guys is around ROS. For those of you who don't know, ROS stands for Robot Operating System. It's actually not an operating system. It's rather poorly named. It is really, it's robot middleware. It's a bunch of software that runs mostly on Linux computers, Ubuntu Linux in particular. And it provides a framework that allows a lot of different programs to communicate by publishing and subscribing messages. It's a very, very powerful architecture. It's probably been around since, 2008 or 9. Nowadays, most robotics labs use it, and a number of robot companies use it. Baxter Robot, for instance, is based on ROS. And because it's this one common environmental framework where programs can communicate with one another, people have built some awesome ROS capability. We call them ROS nodes. So you can find nodes that can read from cameras, that can read from laser scanners, that can drive robots, that can do path planning, that can do map building. There is a huge range of really capable, well-tested code that's written for the ROS environment. Generally, if you want to write a program that plays in the ROS environment, you're going to write it in C++, or you're going to write it in Python. You can also write in Java, but Python and C++ are what most of these packages are written in. Now, until recently, if you wrote a program in MATLAB, you were disconnected from the ROS world. You could do some stuff in MATLAB, maybe you get your code working right, and then you'd rewrite it in C++ or in Python and build it into a ROS node, and away you go. Very recently, in MATLAB release 2015A, which only just came out, I think, last week, there is now a thing called the Robotic Systems Toolbox. And this is a bunch of functionality that allows MATLAB programs to communicate with the ROS framework. So there are functions that let you read a topic. There are functions that let you write a topic. You can even, in the Simulink environment, you can create block diagrams where you have an input block, reads a topic comes out on a wire, you do some stuff with it, and then you push it into a publish block, and that then sends it out to other ROS nodes that care about that particular topic. And you can actually run that Simulink diagram, and that then becomes part of a ROS system. So your MATLAB/Simulink environment is now part of a bigger robotic system built on ROS. So that's pretty cool. But even more cool is the fact that you can now export that Simulink block diagram, and it will chug out a bunch of code which you can compile, which is a standalone ROS node. So you can draw it in the block diagram language, export it as a bunch of code, compile it, and then run it, and it's just like any other ROS node, but you created it inside the MATLAB environment. So there is now the ability to have robotic algorithms written in MATLAB playing with real-time stuff happening in the ROS world, and that's a fantastic development. To say, it only came out a week ago. I think once people learn about what it can do, it will start to become quite widely used. I like MATLAB. I've used it for a long time. I find it very convenient. If I want to write a piece of code, there aren't lots of definitions and include files and all the cruft that I need to include if I'm writing C++ code or Java code. I can just get straight down to the problem at hand, and I find it a very forgiving environment, fantastic maths, fantastic graphics, and I find it personally a very productive way to work. So that's it for sort of languages, MATLAB and ROS. Next question is from Troy Wu, and he asks a bunch of questions. First of all, he's wondering if I'm still recording next week's lectures at the moment, and whether I can adjust next week's lectures based on this week's feedback. It's a really good question. The lectures have been recorded in a rather odd order, and certainly most of the lectures that are coming up were recorded last year. There's only a few oddments, like lecture 12 I recorded a few weeks ago, but most of the rest of the lectures in the coming weeks were all done last year. And the robotic vision MOOC, which is the MOOC that follows this one, that was certainly all recorded last year as well. So sadly, there isn't the option to adapt feedback and comments from previous weeks into the pre-recorded lectures. What we're going to do though is look at all the feedback, and it's great feedback on the lectures to date, and where there are lecture sections that need to be updated. They go onto a rework list, and when we get the chance, we will revise or update those lectures where there are errors of fact that people pointed out. Next question Troy asks is, how long does it take to shoot each video, and are there any bloopers? There's a lot of bloopers. What I do is I basically prepare the lectures. I'm a Mac person, so they're all prepared in Keynote, basically one big presentation. Once upon a time, this was a lecture. It was a 1-hour lecture that I gave to my class here at the university. So we've chopped it up into these different sections, and I record each section one by one, and I narrate them. I go through the slides and I narrate them. Now, I'm not scripted, so I just talk. The slides come up and I just start talking. And typically each lot of talking is 2 to 3 times longer than what it is that you witness in the MOOC. So that the rest of that is just junk, and it gets lost during editing. So I'm going along and I make a mistake, or I think I haven't explained it very well, so I go again. Sometimes I go again. Sometimes I go again. I think one 10-minute section once, I think the worst one took me an hour to get right. And probably it would have been better if I scripted them and read the scripts, but my fear is that it's perhaps a little bit wooden if I did that. And it's also not the way I give my lectures. When I give my lectures in class, the slides come up and they kind of prompt me, and I just all blurts out. And so I've done exactly the same thing in the MOOC narration. So it's not very efficient, and some of the bloopers are probably amusing, and maybe one day we'll make a blooper reel and put it out. Troy, question number 3 is, what recording equipment do I use? Basically, I go to a little video conference room, a quiet room in the university. My office is not quite quiet enough to do this stuff. And I just wear a pair of Sennheiser headphones with a boom microphone. And so that's the recording equipment. I'm not using the microphone in my screen. I actually use a headset microphone and headphone combination. So I experimented with a lot of different microphones, and that is the one that seemed to work best. Troy asked, what screen caption software am I using? So I use a package called Camtasia. So it does the screen capture and the audio capture. We then go through and edit out all the bloopers, and then I add extra animations or annotations on top of what it was I recorded. And that takes quite a long time as well. So, you know, a 10-minute segment might take me 20 to 30 minutes to record. It can take 30 to 60 minutes probably to go through and edit out all the junk and to add the annotations. So it's a very massive project. So if you want to do an online course, you have to really want to do it and be incredibly committed to it. And then finally he asks, what video encoder am I using? I actually don't know the answer to that question. I'm sorry, but we recorded everything we could at 1080p. So we went for the best resolution that we could. I know that some of the MATLAB screencasts, the text is quite small, but so I can get enough on the screen to explain what I want to explain. If you do look at it full screen, you can certainly see all of the details. So we tried to do everything we could at the highest possible resolution. And that's available to you as viewers if you need it. All right, so that's Troy's question. Thank you. A question from Christine Niebler, and she asks, in what ways could robots help us with the growing elder population, and how could robots avoid people becoming lonely? And then she also asks, what are the most urgent problems to be solved in medical robotics? This is a really interesting question. We talk about this again in lecture 12, and actually quite a lot of the questions that come up today are things that we'll cover in lecture 12. Lecture 12 is all about how robots fit into society. Why are we talking about robots and creating robots? You know, to what end, to what useful purpose? And that's a really complex question. I certainly don't have all the answers to that. So lecture 12, we touch on these things, not necessarily with answers, but certainly with a lot of questions. So Christine's question is a really good one. One of the issues with the growing elder population is there's a ratio of the people who we call dependents. So that's young people and elder people who are not working and need to be looked after. They need to be fed and housed and all of that. And then there is the working population, you know, people between 20 and 60 who do the work. And part of that work is to look after the dependents. So there's a critical thing called the dependency ratio. And at the moment, that's pretty good. It's about as good as it has actually ever been. But it's going to quite quickly go bad in almost all countries. So we're going to have this problem where the number of dependent people in our society, you know, will exceed the number of working people. And so really the only solution to that is to increase the productivity of those people who are working. One way to improve people's productivity is to introduce robots into the workforce. That's what we did in car manufacturing. Once upon a time, cars were completely made by people. That, you know, over time became more and more expensive, but we could make the people individually more effective, more productive by throwing robots into the mix. So I think, you know, that's one way that robots could potentially help us with a growing elder population. Can robots stop people feeling lonely? That's a really interesting question. Human beings have a remarkable ability to connect at an emotional level with almost anything. I mean, with their motor car, with a pet, even with inanimate objects. So it is possible that people could perhaps feel connected to machines, robot machines, and particularly if these robot machines are human in appearance, then, you know, perhaps that would happen. At our lab, we have a number of the Now robots. These are little Aldebaran humanoid robots. I don't know, they're about maybe 1/2 meter tall. And everybody who sees these things just falls in love with them because the Now robot looks up at them with these big, adoring eyes. People's hearts melt and they want to pick the robots up and cuddle them. It's quite extraordinary. So there's something just in the appearance of these machines that messes with the way people's heads are wired and makes them feel an emotional attachment to the machine. So it's entirely possible that we could use human-looking robots to emotionally bond with people and cure their loneliness. It's a question about whether that's the right thing to do or not. So maybe it could happen, but we need to have a conversation about whether that's the right thing to do. What are the most urgent problems to solve in medical robotics? I think the most urgent problem in the whole healthcare system is its cost. In my country, we have continuous debates about the cost of healthcare and whether as a country we can afford to provide the healthcare that we do to the population. This is probably a conversation that happens in many other countries around the world. As the population gets older, the cost of healthcare is only going to go up. We live longer, more elderly people, it's going to be very expensive. So once again, the only way you can make things cheaper is to improve the productivity of the people who provide the service, healthcare workers, and that could be by augmenting them with robotic aids. And there's lots of jobs in the healthcare system that are pretty menial. So you look in a hospital, thousands and thousands of people doing all sorts of things. Maybe robots could do simple things like change beds, take the linen off, make a bed, lift a patient from a wheelchair into a bed, off a bed into a wheelchair, take people to the bathroom, all sorts of things that perhaps don't require a huge amount of skill. Robots did those, free human beings up to do things that require knowledge of medicine, real human communication skills, empathy, and so on. So lots of scope. The big issue is how do we reduce the cost of healthcare, keep that quality of the healthcare there, but reduce its cost. The next question, Yogesh Saini asks, as industrial robots get more sophisticated and can handle more complex tasks, what are the chances of robots eliminating workers in the manufacturing industry? And it's a really good question. And it's a complex question, but the answer is, I think that as robots come in, yes, they will displace some workers, and that's uncomfortable. And clearly it's unfortunate for the workers who were displaced. But the story is a bit more is more complex than just that. So let's consider a country. Let's consider the United States. And the United States builds a lot of automobiles. And the automobiles are built by people and robots. If the cars were built just by people, they would be so expensive that no one would be able to buy them, because labor in the United States is much more expensive than labor is in the East. So if the decision was made that you would have no robots in car factories in the United States, then that industry would probably fold, and the United States would import all its cars from Asia. So by having some robots in the factories, the productivity goes up, you maintain a viable industry, and that employs some people, it generates wealth, and it pays taxes. So actually it's a good thing to have. So that's one thing that you need to think about when you talk about robots and jobs. Another one is that every time there's a technological revolution, some jobs are destroyed and new jobs are created. So when Gutenberg invented the press, that was fantastic. That made books available at a really low cost, and it helped spread knowledge to not just rich people, but to everybody in society. So you'd have to argue that Gutenberg's invention of press was a great thing. But before that, books were transcribed manually by monks. So probably after Gutenberg's press, then there's a lot less call for monks to transcribe books. So great for knowledge transfer to ordinary people, bad for monks. Another story is when radio was invented early last century, it did terrible things to the piano industry, because before the invention of radio, people used to play pianos of an evening and sing. Radio came along, music was available, nobody had to play the piano, and piano sales just dropped, just decimated the piano industry. And there are countless examples of that. The invention of the automobile made less work for people who delivered hay to feed the horses, less work for blacksmiths making horseshoes. So, and so it goes. For every technological revolution, there are winners and losers. So for the introduction of robotics, yes, some people who work in manufacturing, some jobs will be lost. but other jobs will be created. What those jobs are at the moment, I can't see, but I'm sure they will be there. And so yeah, maybe that's, I've probably gone on long enough talking about robots and jobs. We'll talk a bit more about this in lecture 12. And if you've got ideas or strong views on this business of robots and jobs, then start a thread in the discussion forum. I'd certainly like to be having these kind of discussions in week 6. But if you want to start those discussions now, go #jobs and start having a debate about robots and jobs. All right, I've got a list of questions that Obadiah printed out for me. What do I have here? Vadi Mysore asks, all roboticists should have advanced knowledge of mechanical engineering and computer science. Is not this correct, especially for advanced research? Look, it's a good question. I think, so the question is about mechanical engineering and computer science and what's the balance of those things in modern robotics research. Probably to this, you should add electronic engineering, because really a robot is a mechatronic system. It comprises mechanical components, electrical components, and software. To my mind, at the moment where we are in robotics, we have good enough electronics and we have good enough mechanicals, right? There are a lot of robots that you can buy now from a number of different companies. And they're great. There are great mobile robots with wheels. There are fantastic flying robots you can buy. You can buy great robot arms from a number of different companies. They might perhaps be a bit more expensive than you like, but high quality mechanical and electronic hardware is there. Really, in my view, the big challenge in robotics today is in the algorithm department. It's the software, the algorithm, the smarts, if you like, that's severely lacking. So I think if you look at most advanced robotic research today, the bulk of it is in terms of software and algorithm design, creating, implementing real-time systems, large distributed systems of software that actually make the robot work. Now, there's some fantastic work happening in design. Some people are doing some wonderful mechanical design of robotics, amazing flying robots and crawling robots and so on. So there is work in mechanical design, but to my mind, the biggest challenges we face are around the intelligence, the smarts, the perception, and that's really algorithmic and software work. Next question, sort of also related to education. Ersan Renato asks, do I think that control engineering should be a major, standalone discipline separated from electronic engineering? It probably is in a number of institutions. Control engineering probably is a standalone discipline. At my own university, it isn't. It's embedded into electrical engineering, mechatronic engineering, and aerospace engineering. It doesn't stand alone, but it certainly could, and in some places, I'm sure, in fact, that it does. Okay, next question is an interesting one. Renato Langersek asks, was I ever emotionally attached to one of my robots? And no, but I probably do tend to anthropomorphize robots. I tend to refer to them as him and imply human-like characteristics to it. Like I talk about what was the robot thinking and so on, which is probably not technically correct. I think arguably a robot isn't thinking anything, but I probably attribute characteristics like thinking, emotion, and agenda to the robot. So perhaps not emotional connection, but I probably treat them perhaps a bit more like people than I should. All right, next question. Drev Rathor asks what type of robots we can build on completion of the course, and also to tell us what part is not introduced in these lectures. All right, so that's a really good question. And today there are lots and lots of different sorts of robots. And this course, the first couple of weeks, talked about fundamental concepts about how do we represent pose, orientation, so on. That's common to all robotics. But the rest of the course is about arm-type robots, robot manipulator arms. And these are the earliest type of robots that we created. And these are sort of robots that you see doing useful work in factories, building cars, building circuit boards. And that's the focus of this course. We don't talk about mobile robots. And that's a really big area of robotics these days. So these are machines that move on the ground or on the water or through the air. And there are important questions about how does a robot work out where it is? What's its location in the world? How does it plan a safe path from point A to point B so they can get its job done without colliding, perhaps in an energy efficient way? So mobile robotics is a really big discipline, and I don't cover that at all in this course. There are a few in my textbook. There are 3 chapters that talk about mobile robots, and I have a really strong desire to do another MOOC on that topic, but that's not going to happen until 2016 at the earliest. So I don't cover any kind of mobile robotics in this particular course. So by the time you get to the end of this course, then I hope you know enough to be able to build an arm-type robot. And the project that we've set in the course is to build really the simplest type of arm robot. It's only got 2 joints, and it operates in a plane. So it just moves a pencil across a sheet of paper. If it had only 1 joint, then I don't think you could really call it a robot. So we're getting you to build a robot with 2 joints. And if you got really enthusiastic about this, then you could extend it to 3 joints. Maybe you could make it move in 3 dimensions instead of just 2 dimensions. So there's a lot of scope, but this course is going to take you only as far as simple arm-type robots. Next question. Hariprasad Kandiraju asks, could I suggest a method or suggestions on how to get updated with research in the robotics field? This might depend a bit on where you are and perhaps what your educational situation is. Are you a high school student or an undergraduate student or a research student? Typically, the way that PhD students and researchers get updated with what's going on is to read technical journals, which tell you what's happening in the field. There are magazines that you can subscribe to. The IEEE has a Robotics and Automation Society, and they have a very readable magazine which tells you a lot about what's going on in the field. They also have a number of journals. So if you're an undergraduate or graduate, you could join the IEEE, join the Robotics and Automation Society, and get access to information that way. A really good way is to go to a conference. At a conference, you can sit in a technical session, you can hear people talking about their research, and you can get to meet them during the breaks and have great conversations. So there is the ways that I know about connecting to state-of-the-art research. If you're a student at a university, your university may well have subscriptions to a lot of these IEEE publications. Other publishers, Springer and Elsevier, also have robotics journals. So if you look in your university library system, enter the keyword robots and find what publications they've got, what books they've got in their library, ebooks, paper books, and start reading some of those. These are all good ways to get up to date. All right. Let me. A technical question here from Michael Stevens, and this is related, I think, to Lecture 5 when we were talking about accelerometers. And there is this very unintuitive concept that I tried to get across in the lecture, and that is if you sat an accelerometer on the desk, on the table, and it's not moving, it's going to report an acceleration of 1g upwards. That's completely unintuitive because the device doesn't look like it's accelerating. It's not moving. So Michael's question was, if I dropped an accelerometer, I had it here and I let it go, what acceleration would it read while it was in free fall? And he asks, would it be 0? And yeah, that's right. It would read 0g. That would be the acceleration that it would indicate. And again, that seems unintuitive because it's accelerating under the influence of gravity. The device is actually accelerating. It's called an accelerometer. Why is it reporting 0? So you need to go back to a fundamental understanding of what it is that an accelerometer actually measures, how it works, to understand why that would be the case. That that feature of accelerometers is widely used, particularly in older laptops before solid-state discs became so popular, that if you dropped your laptop, you knocked it off a desk, the laptop would detect that it was in free fall using information from accelerometers, and it would use that information to, let me just need to move my mouse here, it would use that information to retract the heads on the hard disk so that it wouldn't damage the hard disk. So yeah, an accelerometer in free fall is going to indicate 0G. So yeah, Michael got that right. Maybe this will be the last question, and this is from Payush Gaurav, and he's talking about the work of Hugh Hare at the MIT biomechatronics lab. And in Hugh's lab, they do a lot of work with prostheses. So you have something, if you've lost a limb, you replace the missing limb with a robotic device. And how can these be connected to the nervous system of the body so that you could control this robotic device? Say I had a robotic hand on the end. So I chopped off here, and I've got a robotic hand here instead. Could that be connected to the nervous system? And yeah, there's been a lot of research in how you, and I believe, this is not my area, but I believe there have been demonstrations of prostheses which are connected directly to the nerves. So you think and try to move in the way you used to, and the nerves are activated, and the hand does the right thing. If I have a recollection that you need to sort of relearn a lot of the motor skills, but that it can be done. So there's a lot of work happening in this whole area of connecting biological systems to robots. So that particular example, I believe people are making good progress in that. I've also seen, I think on YouTube, a monkey with perhaps some implants in its brain that was controlling a robot arm. And just by thinking the right thoughts, it could make the robot arm move out and grab some food and put it into the monkey's mouth. So that's another example. People have also done work with simple insects like cockroaches, and actually injected signals into the nervous system of the cockroach to make it move the way you want it to move, rather than what the brain of the cockroach wants the creature to move. So there's a lot of stuff happening in this area of connecting computer systems to biological systems, and it's not my line of research. It's interesting, but I don't really keep very much abreast of it. I've been talking for 45 minutes. That's probably more than enough talking from me. Look, there's some really wonderful questions. Thank you very much for sending those in. As I say, I'm pretty much out of time. Next week, as I said, we want to try and have an event where the focus is very much on the groups. In order to do that, we need to hear from the groups. So those of you who are working away in many of the active groups inside the discussion forum, we'd really like to hear from you, and particularly find out how we can get some representation of what it is you're doing, be it a few slides, be it some videos, and be very happy to reflect that back to the whole MOOC cohort. And maybe if you've got questions as well, send those in, project-specific questions, send those in, and we'll get the TAs, Jack, Obadiah, and James, to answer some of those. So until next week, thanks very much for being here, and I hope you continue to enjoy the course. Thanks very much. Bye.